This is MAT 5700 Lecture number 40, and today we will begin Chapter 7, which is about properties of expectation for more than one continuous random variable. I'm not going to cover every part of Chapter 7. I'm only going to cover the parts of Chapter 7 that we need to do the material in Chapter 8. That's because we're near the end of the term, and secondly, we never cover the other parts of Chapter 7. So let's start off with some motivation from something you know already that we actually did cover, is that if you have, let's recall, if you have a continuous random variable x, and g of x is a function, then you can apply the function to the random variable x to get a new random variable. And we could ask what its expectation is, and the expectation of this new random variable g of x is given by integrating from minus infinity to infinity g of x times f of x dx, where f of x is the PDF of the random variable x. We proved this way back when. I don't remember which chapter. So there's a generalization to more than one random variable. So this is the generalization. It's a proposition in section 7.2. And I don't remember the number of the proposition, unfortunately. So the proposition is the following statement. So let x and y be continuous random variables with joint probability density function f of xy, and let g of xy be a function. I think it should be continuous, really. Well, let me just say a function. Probably continuous. So then the conclusion is that if we form this new joint probability, we formed g of xy is now a random variable in its own right, and we could look at its expectation, and this is a double integral from minus infinity to infinity, minus infinity to infinity of g of xy times f of xy dx dy. So you're integrating over the whole plane. And this is, the proof of this is very similar to the proof that I gave, at least when g of x was non-negative, of the previous statement. So, but this is the statement that's relevant for us right now. Okay. So, so now you can use this fact, this thing we just stated but did not prove, to actually prove a whole collection of statements, which are extremely useful, it turns out. So, for example, let's consider the following. So let's let x and y be continuous random variables, CRVs, in other words. Then the expected value of x plus y is the expected value of x plus the expected value of y. So this is using the function g of x. And by the way, I should have said here, well, I don't have to say anything. This is a true statement. And and here g of xy is the sum function, x plus y. Okay, so so more generally, for a bunch of continuous random variables x1 through xn, we get the expected value of the sum of all the random variables is the sum of the expected values. So it's E of x1 plus E of x2 all the way E of xn. Okay, so I might as well just prove this for you directly. Let me prove the first statement directly. So what is the expected value of x plus y? Well, that's by definition the integral from minus infinity to infinity minus infinity to infinity. This is actually not the definition. This is the proposition x plus y times the joint density function. On the other hand, we can break up the integrand into x times f of xy plus y times f of xy. And so this becomes minus infinity to infinity minus infinity to infinity x f of xy dx dy plus the integral from minus infinity to infinity minus infinity to infinity of y f of xy dx dy. So now if we integrate the if we look at these integrals, we can play around with them. We can see that, for example, that if we do the this integration here, if we reverse the order of integration to make a dy dx, which we're allowed to do, then integrating, and we can bring the x across because x has nothing to do with y. So I can put here the x outside the integrand, the inner integrand. This term, this inner integral now is the definition of the marginal probability density function of x. And likewise, a similar calculation shows that we can bring the y across from the second integrand. And then the inner integral is then the marginal density function for the random variable y. And so then this becomes the integral of x times f sub x of x dx, which is the expected value of x. And the second integral is the expected value of y, and that's it. That's what we had to show. Okay, and the other statement with n of these is just something you can do with the so-called principle of mathematical induction. I'm not going to prove it. Okay. I'd like to make a definition now. Okay, so I'm going to make a definition. So let's let x1 through xn be continuous random variables. Okay, now we already defined what it means for them to be independent. Recall, these are independent if the joint PDF f of x1 through xn, it breaks up as a product f sub x1 of the random for the x1 random variable times f sub x2 of x2 and so on. So the marginal PDF breaks up as a product. I mean, the product of all the marginal PDFs equals the joint PDF. That's what it means to be independent. Now I will say that x1 through xn are identically distributed if they have the same if they have the same PDF. So f sub x1 of x, f sub x1 equals f sub x2 of x, etc. They have the same distributions. So if x1 through xn, the random variables, are both independent and identically distributed, so both properties hold. So let me, independent and identically distributed, we say that, well, we shouldn't, it's not saying, we abbreviate this property by indicate that by writing the expression IID, independent identically distributed. Okay, so that is just language. Okay, so here's another application of the proposition. So if x1 through xn are independent and identically distributed, continuous random variables. In fact, they don't have to be continuous, they could be discrete random variables. This is always true. Then we set x bar equal to the average. So that would be the sum of xi over n, where there are n of these random, this is the n. Okay, so I want to form the sum of the random variables. There are n of them, and divide by n. So this is the so-called sample mean. Xi, let's say xk over k. Let's write it like that. K goes from 1 to n. So this is the so-called sample mean. And we can now compute the expected value of the sample mean by means of the proposition. So this is the expected value of the sum. This is actually wrong. Terrible. What I meant here is the sum of all the random variables, x sub k goes from 1 to n, and then I want to divide everything by n at the end. So this is 1 over n times the sum of x sub k. K goes from 1 to n. Okay, so now we can bring the 1 over n outside, and this is the expected value of the sum x sub k. And we know that this is the expected value and the sums commute with each other. So this is e of x1 plus e of x2, etc. But these are identically distributed. So let's set mu equal to the expected value of e of xi. They're all the same, right? Because these are identically distributed. They have the same means. So this is the same as e of x1, e of x2, etc. So this is n times mu, n copies of mu times 1 over n, which is equal to mu. So in other words, the conclusion that we have is that the expected value of the sample mean is the actual mean of the identically independent, identically distributed random variables. So that's kind of cool. Okay, so what I'd like to do now is an example in 7.2, which is for the binomial random variable, which is more of the same in some sense. So let's clear the screen. Okay, so let's suppose X is binomial of type BNP. Remember, this comes about from a Bernoulli trial, a successive n Bernoulli trials where we say flip a coin n times, where the probability of heads is P. So if we let X sub I be the random variable, which is 1 if on the ith trial, the ith time you do the experiment, success occurs, and 0 if failure occurs, so otherwise, in other words. So then X, which is binomial, is the sum of X1 plus X2, because we're adding up all the successes. Okay, so we've done n experiments, and we're adding up these random variables. So then the expected value of each xi is, the xi's are IID, because each one is, the trials are supposed to be independent of each other, and the coin that you're flipping is the same coin, right? So E of xi, we can figure out what the expected value. This is actually a discrete random variable we're looking at. So the expected value is success with probability P. So that gives you a 1 with probability P and a 0 with probability 1 minus P. So in other words, the expected value of xi is P. So the expected value of X is given by the expected value of the sum of the xi's, which is the sum of the expected values of the xi's, which is the sum of p's and how many copies of p you have, n of them. So this is n times p. So we've actually derived this formula before differently, but this shows you the expected value of a random variable of type BNP is NP. Okay, so that is all I wanted to cover in section 7.2. I don't want to cover 7.3. I'm going to go directly to 7.4, which is a very important section in the text. So 7.4 is about something called covariance. Covariance. So let me point out, first of all, before I start, we have a proposition in this section, which is called 7.4.1, which says that if G and H are functions of one variable, and X and Y are continuous random variables, then we can look at G of X times H of Y, and we can take its expected value, or we can take the expected value of G of X and multiply by the expected value of H of Y. Now you could ask whether they're the same or not, and the statement is if X and Y are independent, then these are the same, these give you the same thing. Okay, so I'm going to give you a proof in this, but let me point out in a note that if G and H are the identity functions and X and Y are independent, then we get the statement that the expected value of X times Y is the expected value of X times the expected value of Y. And I believe we actually saw that at one time. Okay, so let me give you a proof of the proposition. So it goes like this. The expected value of g of x times h of y is by the proposition, the integral, the previous proposition that I stated today of g of x times h of y times the joint probability density function. But now the joint probability density function is a product because x and y are assumed to be independent. So this would be f sub x of x times g sub y of y, and then dx dy. Well, we can now use the Fubini theorem. We can break this up as the integral from minus infinity to infinity of g of x times f of x dx times the integral from minus infinity to infinity of h of y times it's be f sub x of x times, oops, I have a notational mistake here. I mean a probability density function here, not a g. Here's the correction. So f sub y of y dy, and this is by definition the expected value of, not the definition, but a theorem, a proposition we proved way back when, and that's what we needed to show. So that's it, we did it. Okay, and so this leads to the following interesting definition. Remember that in this proposition that we just proved, we have an assumption of independence. So if they're not independent, we cannot expect this equality here to hold, and that we're going to use that to our advantage. So here's the definition. The covariance of continuous random variables x and y is given by the following expression. It's the expected value of the product minus the expected value of x times the expected value of y. Now, if x and y were independent, then the covariance would be zero by what we said already. So so the covariance being zero gives you evidence that the random variables are independent. In other words, if the covariance, if we write this in the contrapositive way, is not zero, then x and y aren't independent. So it measures the degree to which the random variables are independent. Okay, so I'm gonna end on some properties of covariance. So the first property is that the covariance of x comma y is the same as the covariance of y comma x. Okay, let me box the formula for covariance. This is the definition. Okay, so secondly, if we take the covariance of x with respect to itself, we get the expected value of x squared minus the expected value of x times the expected value of x, but that's exactly the variance of x. Okay, third property, which is pretty clear from the definition, and I won't prove it, is if I take the covariance of a times x with respect to y, then you can bring the A right through, A times the covariance of X, Y. So this is the this is the third property. And now we have another property, which I'll call property 4, the covariance of any sums, covariance of summation xi, summation yj. So we're taking sums in both slots of different random variables. This breaks up as a big sum over I and j of the covariance of xi times yj. How many terms are there? Well, if there are, say, n of the x's and m of the y's, there are mn terms that it's broken up into. Okay, I would like to add one more property to all of this, which the book really uses as the definition, but I think it's better to make it a property. The covariance of x and y is the same as the expected value of x minus the expected value of x times the expected value of y minus the expected value of y. So this is actually the book's definition of it. I don't make use of this very much, this particular formula. Okay, so that's covariance, and we will return to study more properties of the covariance in the next lecture.